Welcome to the lecture titled Steady State Gain from Asymmetrical Relay Test. In this lecture, we shall derive some explicit and exclusive expressions meant for getting the steady state gain from the relay test. The asymmetrical relay test will result in asymmetrical output, and we have attempted earlier to measure 4 parameters on the asymmetrical output. Now, we can make use of the asymmetrical output and input to the system to estimate one more parameter associated with the transfer function model. Now, the transfer function model is G s is equal to k plus minus T 0 s plus 1 times c to the power minus theta s upon T 1 s plus minus 1 T 2 s plus 1. So, the transfer function model has got 5 unknowns, and those are the steady state gain k, the 0 T 0, the time delay theta, and the 2 time constants T 1 and T 2. So, in all we have got 5 unknowns, but so far we have been able to make 4 measurements on the asymmetrical output of the relay system. Now, those measurements are AP, the peak amplitude of the output signal, AV, the negative peak amplitude of the output signal, and 2 zero crossings, those are namely T 2 and T 4. And we have also found that at time T 2 x T 2 is equal to 0, and at time T 4 x T 4 is equal to 0. Thus, the 4 measurements have enabled us to estimate 4 unknowns associated with the transfer function model using 4 nonlinear equations. In this lecture, we shall try to develop analytical expressions that can be used to estimate the steady state gain associated with the transfer function model. What is steady state gain? When s tends to 0 or the frequency of a system output becomes 0, at that time G 0 becomes k, and that is known as the steady state gain. How can we find the steady state gain? For that, we have to concentrate on the asymmetrical output, and if I concentrate on one period of the asymmetrical output, the area of the asymmetrical output can be obtained conveniently using the analytical expressions we have derived earlier. So, what will be the area of the asymmetrical output for one period? This will be the area for the asymmetrical output. Let us denote the asymmetrical output by the symbol a y. Thus, a y can be given in the form of an integral which is starting from time t 0 to t 4 with y t dt. So, that will give us the area of the asymmetrical output signal, whereas the area of the input signal can be also obtained, where the input signal area of the input signal can be shown as this one. So, then we have to make use of this to find the 2 areas, where u will be the areas for the input signal, area for the input signal, and next the ratio of the areas will give you the steady state gain. So, k will be equal to a y upon a u. So, all these things will be developed in sequence. Now, I will start with the asymmetrical output first. So, the output will assume this form for one period of time. Now, y t is the output, and I will denote different time instants to find the area of this signal. Now, I will start from time t equal to 0 till different span depending on the type of input signal we have for the system. So, this is our input signal, which has got a number of piecewise constant inputs during different instant of time. Now, what is this? This is our theta. So, this span is denoted by theta, and here we get the period tau, and for the full period we have got tau p starting from time t equal to 0. to find the area of this signal from time t equal to 0 to tau p. Now, I have to write the expression y t is equal to integral from 0 to tau p y t dt. Sorry, not this is not the output, this is the area of the output. So, I write a y is equal to integral from 0 to tau p y t dt. Now, how to find y t for different time segments, because we have got different type of inputs, a number of piecewise constant input to the system. Therefore, the output during that particular piecewise constant input has to be found initially. So, this has to be expanded and written in the form of integral from 0 to theta y t dt plus theta to, I will start from here till we go to this point. So, that will be our tau plus theta. So, we go from theta to tau plus theta y t dt plus tau plus theta to tau p y t dt. This will give the three terms combined together will give us the area of the output signal. To find the area of the output signal, I need to find the state of the system at different instant of time, because we know that the output can be found using the state variables x t, where y t becomes c x t. C is the constant of the dynamics of the second order plus dead time system. Now, for that I will start deriving the state equations for different segment of time. So, we know that the solution of a state equation is given by the general expression x t is equal to e to the power a t minus t 0 x t 0 plus integral from t 0 to t e to the power a t minus tau b u tau minus theta d tau. This is what we get for the dynamics of a system at any instant of time, where x t stands for the state of the system, as you know. Now, since in our case luckily we have got u tau minus theta is a constant, either h 1 or minus h 2, using that it is very convenient to find the second part of the x t, which becomes t 0 to t e to the power a t minus tau b h 1 d tau or minus h 2 d tau. So, let us take u tau minus theta is equal to h 1, which results in the integral part h integral from t 0 to t e to the power a t minus tau b h 1 d tau. So, let me find the integral, which comes out in the form of a inverse. Then we will have integral e to the power a t minus tau with the limits t 0 to t b h 1. When the limit is put, then we get it in the form of a inverse I minus e a t minus t 0 b h 1. So, thus we get the integral in this form. Now, the integral can also be obtained using one simpler expression, which can be given in the form of 0 to t minus t 0 e to the power a s b u s d s. So, either one can use the upper one or the bottom one, because the bottom one gives you very simpler expression compared to the earlier one. Now, the bottom one also can be solved and found as a inverse e to the power a s with the limits 0 to t minus t 0, and you have got u s equal to h 1. So, b h 1, and that will give you a inverse e to the power a t minus t 0 minus I b h 1. So, there is difference in sign only. So, you need not worry about that, because here the integral will be found with respect to e to the power minus a tau. So, obviously, there will be a minus here, and ultimately you get here minus, and which gives you finally in the form of a inverse e to the power a t minus t0 minus I b h1. So, I get the same expression using the upper or the lower integral. So, I shall use henceforth the lower integral in place of the upper one for finding the state of the system at any instant of time. Thus, I can write x t as e to the power a t minus t0 x t0 plus integral from 0 to t minus t0, integral from 0 to t minus t0. Please keep in mind the limits of this integral, which always starts from 0 to the time span for that segment of the input t minus t0 e to the power a s b u s d s. Thus, I shall make use of the lower one, the lower expression to find the output of the symmetrical output of the relay control system for different time spans. Now, I shall start finding the output for different time spans. Let me redraw the output signal once more, so that it will be possible for you to follow the different time spans conveniently. So, the output is given in this form. I will draw the input to the system, y t is the output, t is the time axis, and the input to the system becomes like this for one period of the output signal, where the input has got heights h 1 and minus h 2. Now, as you know, this span is the theta time delay associated with the dynamics of a system, whereas this span we take as tau from here, whereas this span again becomes theta, and finally, period of the output is given by tau p. So, the output y t for different segments can be used using the expression y t equal to c x t. Now, when the output is considered, part of the output is considered for the time range 0 is less than equal to t is less than equal to theta, then the output for this time span can be found using the expression c x t, where your time span is from t ranging from 0 to theta. So, x t again can be obtained using the general expression, which is nothing but e to the power a t minus t 0 x t 0. Then I have the integral for the second part, which is obtained in the form of a inverse. So, I will have c again, c plus c a inverse e to the power a t minus t 0 minus I times b h 1. So, let me write once more. So, the output signal will be given by the expression c e a t minus t 0 x t 0 plus c a inverse e to the power a t minus t 0 minus I b h 1, because the input to the system at that time is this piecewise constant input h 1, for which we have got the output starting from time t equal to 0 till time t equal to theta. So, this part of the output of this part of the signal is given by this expression y t. Now, to find the area under this, let me designate that area by symbol p 1. So, p 1 will be from time 0 to theta y t dt. Then the area can be found now using the expression, yes, I will find the area later on. So, let me find the state value output for different segments initially, then we will start finding the area later on. Then for this time range, we have got the state expression as this one, which is multiplied with c to give the output y t. Similarly, for another time range, which is starting from y t So, for this time range where I start from time t equal to theta and I will go up to time t equal to tau plus theta now. In that case, the state variable for that time range, theta is less than equal to t is less than equal to tau plus theta, the state variable x t is given as e to the power a t minus theta x theta plus a inverse e to the power a t minus theta minus I. Now, b, what will be the input at this time? The input at this time is minus h 2. Therefore, we will have minus h 2 over here. So, upon simplification, which again gives us the expression e a to the power t minus theta x theta plus, or I can write here minus a inverse e to the power a t minus theta minus I b h 2. So, this is what you get for the state variable for the second time range, for the time range t between theta to tau plus theta. Then the area of that time span can be obtained using the output, and in which case the area can be obtained as shown here in the shaded part of the output signal. Now, what is why we have been able to get this expression? Simply I have substituted the u s by its appropriate input. In this case, it is minus s 2. Rest of the things will remain as it is. And what changes have been made to this state equation? We start the output signal from time t equal to theta till time t equal to tau plus theta. Therefore, the t 0 becomes theta. Please keep in mind, t 0 is theta, therefore, you have got x theta over here. But x theta, again we know that x theta is equal to e to the power a theta x 0 plus a inverse e to the power a theta minus I b h 1. How do you get this one? This can easily be obtained if you substitute t equal to theta here. So, when t equal to theta is substituted over here and t 0 equal to 0, one obtains x theta conveniently. So, when this x theta is used over here, finally, I get an expression for the x t as x t is equal to e to the power a t minus theta, x theta will be substituted here e to the power a theta x 0 plus a inverse e to the power a theta minus I b h 1 then minus a inverse e to the power a t minus theta minus I b h 2. So, this is the expression for x t for the time spanning from time t equal to theta to time t equal to tau plus theta. So, let me repeat and rewrite this expression after simplification. So, that x t for the time range theta is less than equal to t is less than equal to tau plus theta, x t will have the final form given by e to the power a tau plus theta x 0 now plus a inverse e to the power a tau plus theta minus e to the power a tau b h 1 minus a inverse e to the power a tau minus 1 b h 2. Similarly, we are left with one more segment of the output signal. Therefore, we have to make use of this concept to find the state variable for the last segment of the output signal. So, the last segment of the output signal can be again shown as time t y t, where the asymmetrical output again is shown in this form and the input to the system is like this. Therefore, the last segment starts from this instant, time instant. Therefore, I have to concentrate the output from here till the 0 crossing. and for that the area again will be obtained by this shaded part. Now, to find the state variable for the system for this time range, time t, this is your tau plus theta. So, this span is now given as tau plus theta, whereas this is our tau p. So, for the time range tau plus theta is less than equal to t is less than equal to tau p. For this time, the state variable will be given by x t is equal to e to the power a t minus tau plus theta x tau plus theta, then plus a inverse e to the power a t minus tau plus theta minus I b h 1 now. Again, what is x tau plus theta? X tau plus theta is nothing but e to the power a tau plus theta x theta plus a inverse e to the power a tau plus theta minus e to the power a tau b h 1 minus a inverse e to the power a tau minus 1 minus I b h 2. What is I? I is the identity matrix of the order of A. So, x t upon simplification can be found in the form of e to the power a t minus tau minus theta. X tau plus theta will be substituted over here. So, finally, giving us in the form of e to the power a tau plus theta x 0, sorry, this is not theta. So, this is equal to x 0, then this is your x 0 plus a inverse e to the power a tau plus theta minus e to the power a tau b h 1 minus a inverse e to the power a tau minus identity matrix time b h 2 plus the remaining part as it is e to the power a tau plus theta minus e to the power a tau b h 1 minus a inverse e to the power a tau minus I b h 2. So, we have got an horrible expression which can further be simplified and written finally in the form of x t for the time range 0 for the time range tau plus theta to tau p. The state variable will assume the form e to the power a t x 0 plus a inverse e to the power a t minus e to the power a t minus theta b h 1 minus a inverse e to the power a t minus theta t minus theta minus e to the power a t minus tau minus theta b h 2, then plus a inverse e to the power a t minus tau minus theta minus the identity matrix time b h 1. So, as expected, the state for the final segment of the output is involving two inputs, two linear piecewise constant inputs h 1 and h 2. As you see here, the input to the system is assuming this form, whereas during this input we have got the output which is going from negative to positive. Therefore, we have got the inputs h 1 and h 2 present in this expression. Now, after finding these expressions, what to do with all these expressions? So, we have been able to find the expression for x t, the state variable for different time ranges, then it is possible to find the area of the output signal using the expression. The area of the output signal, asymmetrical output signal, is equal to integral from 0 to tau p y t dt, which is nothing but for our case 0 to tau p c x t dt. Now, I will divide this into different time ranges as you have seen, because you have got different piecewise constant inputs. Therefore, we cannot have the expressions expressed by single expression. So, that way we have to make use of all the 3 time spans to find the final area of the asymmetrical output signal. Now, this goes from the limits 0 to theta c x t dt plus theta to tau p tau plus theta c x t dt plus tau plus theta to tau p c x t dt. Now, I shall substitute the expressions x t, x t, x t we have found for different time ranges. Now, the integral is for the limits 0 to theta. So, the t is between 0 to theta in this case. Now, for the second part, it is your theta is less than equal to t is less than equal to tau plus theta, and for the third part, it is tau plus theta is less than equal to t is less than equal to tau p. So, keep in mind, one cannot make use of the single expression to find the area of the output signal, because we have got 3 different piecewise constant input to the systems, which changes their magnitude at different instants of time. Therefore, the piecewise constant input are to be considered definitely to find correct expression for the output of the asymmetrical output of the system. Now, I shall go on substituting the expressions for x t for different time range. So, let us write this a y by 3 parts p 1 plus p 2 plus p 3 and try to find the parts individually initially before combining and finding the final area of the output signal. Then p 1 is given by the expression integral from 0 to theta c x t dt, which is again written as now integral from 0 to theta c e to the power a t x t 0, and in this case t 0 equal to 0. Therefore, directly I can write this as x 0 plus c a inverse e to the power a t minus I b h 1 times dt. So, what is this? The c has been multiplied with x t, the state variables of the system, and we have to integrate it for the time range t spanning from 0 to theta. Now, when I start integrating this one, I will find the expression c a inverse e a t with limits 0 to theta with the multiplier x 0. Again, for the second part, it will be c a to the power minus 2 e a t with the limits 0 to theta. Then the remaining part will have the expression minus c a inverse integral from 0 to theta for t dt. Therefore, you are left with t with limits 0 to theta times b h 1. So, which upon simplification gives us c a inverse e to the power a theta minus I times x 0 plus c a minus 2 e to the power a theta minus I minus this will be simply c a inverse b h 1 theta. So, the part p 1 has been found in this form. P 1, let me repeat once more, the P 1, the area part of the area of the output signal given by P 1 is given by the expression P1 is equal to C A inverse e to the power a theta minus I times x 0 plus C A to the power minus 2 to the power times e to the power a theta minus I minus C A inverse B h 1 theta. Then similarly, I can get an expression for P2. P2 is from the integral from theta to tau plus theta C x t dt. Now, the correct expression for this time range when put in this expression gives us P2 h. P2 is equal to integral from theta to tau plus theta C e a t minus theta x theta minus C A inverse e to the power a t minus theta minus I b h 2 dt. So, this integral can also be found like the previous case and simplified to give us finally P2 as C A inverse e to the power a tau minus I times e to the power a theta plus e to the power a theta times x 0 plus a inverse e to the power a theta minus I b h 1 minus C a to the power minus 2 e to the power a tau minus I b h 2 plus C a inverse b h 2 tau. So, keep in mind the last term, interestingly the last term is found in the form of C A inverse h 2 tau. If you go back, see the last term of P 1, again it is obtained in the form of minus C A inverse B h 1 theta. So, the last term of the integrals of different parts are found to have the expression C A inverse B. So, C A inverse B, that is one important observations we have made so far. Now, I will try to find the third part P 3, for which we have the integral starting from time tau plus theta to tau p C x t dt. So, when this x t for this one will be which one? The x t for this one is this one. So, when this x t is substituted in P 3, then we obtain that expression in the form of integral from tau plus theta to tau p C e to the power a t x 0 plus a inverse e to the power a t minus e to the power a t minus theta b h 1 will come here, then minus a inverse e to the power a t minus theta minus e to the power a t minus tau minus theta b h 2 plus a inverse c e to the power a c e to the power a tau t minus tau minus theta minus I b h 1 dt. So, c will not come here because c is there already here. So, when again this is expanded and simplified, we will get an expression for this as P 3 is equal to, I will write the final expression of P 3, which will not be so simple, but let me try to write the whole expression for P 3, which comes out to be in the form of C A inverse e to the power a tau p minus e to the power a tau plus theta times x 0 plus C a minus 2 e to the power a tau p minus e to the power a tau p. No, this will be tau a tau plus theta minus e to the power a tau p minus theta plus e to the power a tau b h1 plus, sorry, this is not plus, minus c a to the power minus 2 with terms e to the power a tau p minus theta minus e to the power a tau minus e to the power a tau p minus tau minus theta plus I times b h2 again plus c a to the power minus 2 e to the power a tau p minus tau minus theta minus I b h1 with the last term h minus c a inverse b h1 times tau p minus tau minus theta. So, again see the last term. Interestingly, when all the parts are added together, what we get? When P, the area is found in the form of a y is equal to P1 plus P2 plus P3, then one obtains C A inverse E a theta minus I plus e to the power a tau plus theta minus e to the power a theta plus e to the power a tau p minus e to the power a tau plus theta times x 0 plus c a to the power minus 2 e to the power a theta minus I plus e to the power a tau plus theta minus e to the power a theta minus e to the power a tau plus I plus e to the power a tau p minus e to the power a tau plus theta minus e to the power a tau p minus theta plus e to the power a tau plus e to the power a tau p minus tau minus theta minus I times b h1 with another term as c a to the power minus 2 I minus e to the power a tau minus e to the power a tau p minus theta plus e to the power a tau plus e to the power a tau p minus tau minus theta minus I b h2 minus c a inverse b h1 theta plus c a inverse b h2 tau minus c a inverse b h1 tau p minus tau minus theta. So, this is the expression for area of the asymmetrical output signal, where we will find that all other parts or terms, then the last three terms becomes 0. When x 0 is substituted over here, we have an expression for x 0 which has been found in the previous lecture. So, when x 0 is substituted over here, then the first term, first few terms get cancelled, leaving us a y h. A y is equal to minus c a inverse b h1 theta plus c a inverse b h2 tau minus c a inverse b h1 tau p minus tau minus theta. So, interestingly, we get only simpler three expressions remaining in the expression for the area of the output signal. This is an important observation. So, how the other parts are getting cancelled? If you look carefully, so many terms are cancelling out, like this one cancelling out, e to the power a theta minus e to the power a theta, leaving us only two terms in the first part. Similarly, e to the power a theta cancelling out, minus I plus I cancelling out, then minus e a tau plus e a tau cancelling out, and leaving three terms there, and here also e to the plus minus a tau, and you have got plus minus I. Then whatever remaining terms you have, upon substitution of the x 0 in that term. What is x 0? X 0 is found to be, in our earlier lecture we have seen that x 0 is given by the expression I e to the power minus a tau p inverse e to the power a tau p minus theta gamma 1 h 1 minus e to the power a tau p minus tau gamma 2 h 2 minus e to the power a tau p minus tau minus theta gamma 3 h 2 minus gamma 4 h 1, where again gammas are there. When the gammas are substituted, finally one obtains x 0 in the form of I minus e to the power a tau p inverse with a inverse e to the power a tau p minus tau minus theta plus e to the power a tau p minus e to the power a tau p minus theta minus I b h 1 with another term minus a inverse e to the power a tau p minus theta minus e to the power a tau p minus tau minus theta times b h 2. So, when this x 0 is substituted here, then the first few terms apart from the last 3 terms cancels out and we are left with only 3 terms. Therefore, the output of the relay test has the final form given as a y is equal to minus c a inverse b h 1 theta plus c a inverse b h 2 tau minus c a inverse b h 1 tau p minus tau minus theta. Then what is c a inverse b? We know that from the state space model of the second order plus date time transfer function model, we have obtained C h, C is equal to k lambda 1 lambda 2 lambda 1 plus lambda 3 upon lambda 3 lambda 1 minus lambda 2 and the other element is minus k lambda 1 lambda 2 lambda 1 lambda 2 lambda 2 plus lambda 3 upon lambda 3 lambda 1 minus lambda 2. So, this is the C vector with B vector we know has got the elements 1 and 1, whereas A is given by lambda 1 0 0 lambda 2 matrix. Now, C A inverse B becomes C A inverse B becomes k lambda 1 lambda 2 lambda 1 plus lambda 3 times lambda 3 lambda 1 minus lambda 2 minus k lambda 1 lambda 2 lambda 2 plus lambda 3 upon lambda 3 times lambda 1 minus lambda 2 multiplied by A inverse B. So, A inverse B will be 1 upon lambda 1 and 1 upon lambda 2. So, when this is simplified, we get k lambda 2 lambda 1 plus lambda 3 by lambda 3 times lambda 1 minus lambda 2 minus k lambda 1 lambda 2 plus lambda 3 by lambda 3 lambda 1 minus lambda 2, which is nothing but equal to minus k. So, interestingly we have found C A inverse B to be minus k. Then A where can be written H. You see in all the 3 terms you have got C A inverse B. So, why do not you take common, then giving us A where H C A inverse B times minus H1 theta plus H2 tau minus H1 tau p minus tau minus theta. But C A inverse B is equal to minus k, therefore, allow me to write here minus k, and writing like that I finally get the expression for A y is equal to k times H1 tau p minus H1 plus H2 tau. So, this is the expression, final expression for area of the output signal. So, whatever might be the area of the output signal, the real output area of the output signal can be easily obtained using this simpler expression, which involves the parameters relay heights and few measurements like first sampling, first zero crossing instant, second zero crossing instant from the beginning, which is considered to be 0 with the multiplication of k. Now, let us try to find the area for the input signal now. Then what will be the area for the input signal? As you have seen, the span for different time instants for the input signal can be obtained looking at the output signal only. And for our case, the input signal appears to be of this form. It does not overshoot. So, we will have a zero crossing at this instant of time. Now, I will write the different spans now. What is this input signal? The input signal is going from y t and u t versus t. Now, this is the span, x axis is not correct now, because I have to start from 0. Let me redraw again, because it is getting confused. To find the input signal, let me plot the output signal first, t y t. So, the y t is like this, and we have got the input signal given by this 0 crossing and this one. Thus, what are the spans here? This is theta. What is this? This span is equal to tau. What is this? This is equal to theta, and similarly finally one period is given by tau p. Thus, if I try to find the area of the input signal, I have to consider the shaded area, shaded part only. So, to find the area of the shaded part, what I have to do? I have to consider the heights h 1 and minus h 2. Thus, area of the input signal A u can be written as h 1 theta, this rectangle. Then coming to the second rectangle, the bottom one, what is its width and height? Height is equal to minus h 2 and width is equal to, this will be tau plus theta minus theta. So, this span will be equal to tau. Yes, and the area of the upper rectangle now can be found as h 1 time tau p minus tau minus theta. So, tau p minus tau minus theta. So, when this is simplified again, what do we get? The expression for the AUH h 1 tau p minus h 1 plus h 2 tau. So, if you look at the expression for AY and AU, let me give you the AY and AU once more. So, AY is found to be k times h 1 tau p minus h 1 plus h 2 tau, and AU is found to be h 1 tau p minus h 1 plus h 2 tau. Thus, the steady state gain k, the steady state gain state gain can be obtained from the ratio of the area of the output to the area of the input. So, this is how the steady state gain of the transfer function model is found. So, when you get the asymmetrical output signal, measure the or find the area of the output signal and area of the input signal, take the ratio of the two, that will give you the steady state gain of the transfer function model. So, let me summarize my lecture now. Analytical expressions for the areas of input and output signals A y and A u have been found. Now, taking the ratio of these two areas, it is possible to estimate the steady state gain of the system. Thus, k is equal to A y upon A u. Why we have been doing so? Because we know the transfer function model, in our transfer function model we have got 5 unknowns. Earlier we had developed 4 nonlinear equations to estimate 4 unknowns. Now, the 5th unknown, the steady state gain of the system can be estimated using the areas of the output and input signals. Any points to ponder? What are the limitations? Any limitation of the proposed technique? Yes, this technique is applicable only when the output is asymmetrical, or I mean the average output A y does not become 0 or A u does not become 0 especially. So, this is one of the limitation of this method, that it cannot be used for sustained oscillatory signal of symmetrical nature. That means, when the output is symmetrical, in that case we cannot make use of this technique to find the steady state gain of the system. Is it possible to extend the technique for simple systems also? Yes, it is possible to extend this technique for simple systems, in which case luckily for first order plus date time systems especially, what happens, one can make one can find the area of half period signal. Unlike the full period signal, one can find the area of half period signal. So, A y dash, and similarly area of half period of the input signal A u dash, and the ratio of the two will give you the steady state gain. That is particularly for first order plus date time systems. That is whereas this technique may not be applicable for large order systems or systems with higher dynamics. Thank you.